Professor Bob Young here again, and we're going to follow up our last video with the exponential growth or decay function, and we're going to talk about some different type of models in this video. So let's look at determining an exponential function to model radioactive decay, because we looked at growth models in the first video, so let's look at some other types that deal with this model. So let's say if we have 600 grams of a radioactive substance are present initially, and 3 years later only 300 grams remain, how much of the substance will be present after 6 years? So we've got our exponential equation here. We want to express this situation using it, y equals y sub naught e to the kt power. We're going to use the given variables to first find y sub naught and then k. So notice we're going to go ahead and put 600 in, since that's the initial amount here, and we're going to say that equals y sub naught at year 0 here. So once again, notice that if we have, let's say, e to the k times 0 power, that's going to just give us here, and I'll go with my colors, y'all know the writing tablet is here, e to the 0 power, and again, anything to the 0 power is 1, so that gives us the y sub naught initial amount is 600. And the exponential equation, the model becomes y equals 600 e to the kt power. Now we're going to solve this exponential equation for k, noting that we had some other information given. So we know when y is 300 at year 3 here, if we plug those values in, as you see in blue, and solve, we're going to go ahead and divide both sides by 600 here. So 300 over 600 will be 0.5 or 1/2 equals e to the 3k power. Then taking the ln of both sides, and we've seen this ln of e to some power so many times, we know what's going to happen to this 3k power, don't we? That 3k power right here, you know where it's going. Whoop, here it comes. 3k will equal the natural log of 0.5, so k will be negative 0.231, that constant there. So we are looking not at growth in this model, but we're looking at decay. So thus, the exponential decay equation is y equals 600e raised to the minus 0.231 t power. So now we can use this based on the given information and project down the line. So after 6 years, plugging 6 in for t, and again, make sure you and your calculators are 1 here, we should get about 150 grams of the substance will remain after 6 years. All right, we're going to talk next about what is called the half-life. So it says analogous, sorry about that, got something stuck in the windpipe there. Excuse me, to the idea of doubling time is half-life, the amount of time that it takes for a quantity that decays exponentially to become half its initial amount. All right, so we're going to look at this. Carbon-14, also known as radiocarbon, is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates. Scientists can determine the age of the remains by comparing the amount of radiocarbon with the amount present in living plants and animals. This technique is called carbon dating. So on your CSI show and stuff, if they find this body that's been out there for a long time, this is how they can determine how long that person, you know, has been dead or whatever. So you can actually use these type things in real life again. The amount of radiocarbon present after t years is given by this model, y equals y sub naught e raised to the negative 0.000121 t power, where y sub naught is the amount present in living plants and animals. So it says find the half-life here. So if y sub naught is the amount of radiocarbon present in a living thing, then 1/2 of that, do you see, would give us the what's called half-life. So for y, we're going to plug in 1/2 y sub naught. All right, now what we can do is we can divide both sides by y sub naught here, and that will leave us with 1/2. These will jump out, and these gone will equal e raised to the negative 0.00012116t power. Take the natural log of both sides, and when that natural log hits e, you know what's going to become of that power there. Here it comes again. Oh, how many of these have we seen? We're going to get the natural log of 1/2 equals that power. And dividing by the number in front of t, the half-life is going to be about 5,700 years. So again, when you put this in your calculator, be careful. You might even need to do this one, put in ln parentheses 1 divided by 2, close parentheses, and then divide it by that number. And make sure you're getting these answers 5,700 approximately. So it says charcoal from an ancient fire pit on Java contained 1/4 of the carbon-14 of a living sample of the same size. Estimate the age of the charcoal. So solving again for t, we're going to let y equals 1/4 of that amount, which would be 1/4 y sub naught. So they're going to give you all kinds of different things to throw at you, maybe some different models and so forth. Dividing by that y sub naught leaves us with a similar e to the negative 0.00012116t power equals 1/4. Taking the natural log, as you will see in this case, the time will be 11,400. All right, now for you physics students here, and we try to make sure we cover as many broad areas to help our students as we can. We're going to do what's called Newton's law of cooling. Now, some of you may never see this, and others may see it in other courses, so we want to make sure you're solid on the math. We don't back down from challenges. So Newton's law of cooling states that a rate at which a body cools is proportional to the difference C in temperature between the body and the environment around it. The temperature F of T of the body at time T in approximate units after being introduced into an environment having constant temperature T sub naught is modeled by this function F of T equals T sub naught plus CE to the minus KT power. So again, we're going to have a negative constant there, do you see, which is going to be a decay. So, you know, as you get a hot cup of coffee or something, it's going to cool after a while. Or C and the K are constants. And let's look at that. A pot of coffee with a temperature of 100 degrees Celsius is set down in a room with a temperature of 20 degrees Celsius. The coffee cools to 60 degrees Celsius after 1 hour. All right, so write an equation to model this data. So first, we must find values for C and K in the formula for cooling. From the given information, when T equals 0, T sub naught equals 20, and the temperature of the coffee is F of 0 equals 100. Also, when T equals 1, after 1 hour, F of 1 equals 60. So substitute the first pair of values in the equation along with T sub naught equals 20. And here's what we're going to get. So we're going to get 100 equals 20. Plus CE to the minus 0K power. So again, when we do this anything to the 0 power thing, it's really C times 1, and we get C here. Subtracting 20 from both sides, C would be 80, and that would be what we're going to put into our model now. Now use the remaining pair of values in this equation to find K. So once you know that F of T equals T sub naught plus 80 e to the minus KT power, we're going to go ahead at time T equals 1 hour, the Celsius drop to 60 here. So we're going to put 60 in there and solve for K. So subtract 20 from both sides here. So let's show those steps as always. And we're going to get 40 equals 80 e to the minus K power. And then we're going to divide both sides by 80 and get 1/2. Now, I don't know why they didn't put 0.5 there, but you could have. take the ln of both sides, and you know what's going to happen to this minus k power here. We've seen it a dozen times in all of our lessons so far. And we get minus k equals the ln of 1/2, dividing both sides by -1 or multiplying both sides by -1, whichever way you want to do it. K is going to be minus the ln of 1/2, which is 0.693. So this is our cooling model here for our pot of coffee. 20 plus 80e to the minus 0.693 T power. All right, now we can do some stuff with this. Oh boy. Find the temperature, let's say after a half hour that your coffee will be. Now remember, Mickey D's, McDonald's did not do this, and they paid the price, and we all paid the price as someone got their lips burned. We all drink cooler coffee now. I don't know. I like my coffee hot. I don't know about y'all out there. But anyway, after a half an hour, we're just going to put 1/2 in for T here and make sure we use our calculators correctly. And we should get about 76.6 degrees Celsius coffee there, which I don't know if I would like it at that temperature because I like my coffee piping hot. All right, and then we can also see how long will it take the coffee to cool to 50 degrees. So we can let that function f of t equal 50 and then solve the other way. So they're just going to take and go back and forth here. So we can subtract 20 from both sides. So in our model, we'll end up with 80e to the minus 0.693 T power equals 30. Divide both sides by 80, because again, we want to get this down to the E, and I bet you all know what's coming next. I bet you we're going to ln both sides, as we show here in this next graphic. And it'll take, when we do this and put it in our calculator correctly, about 1.415 hours, or about an hour and 25 minutes. So you can use exponential and logarithmic growth and decay in the real world. And we're seeing more and more businesses, folks, they don't want students who can just solve for X or T or whatever. They want you to be able to apply this to real world situations. So we're starting to get to that as we go up the chain in math. Bob Young signing off. You know what to do now. Hit that homework.